And it's my great pleasure to welcome Kutyniok, who's one of the kind of world leaders in the modern mathematical theory of machine learning. So Gita, over to you.
Yeah, thanks so much for the invitation and for the nice introduction. Let me start by sharing my screen. Let me see.
That looks good.
Okay, yeah, I think now should look good. Okay, yeah, I want to briefly talk about, let's say, the mathematics of artificial intelligence. You know, artificial intelligence is real. I mean, it's a huge application area, and I think very exciting mathematical questions come out of there, in particular then also in the direction of pure mathematics. And so I would like to just show you a couple of samples in that direction. And I think the exciting thing is that basically all of mathematics is required for tackling, let's say, the problems we face there in artificial intelligence. So AI, I think, is changing our lives on a daily basis. We see it around us: robotics, telecommunication, also the whole legal system, everywhere area in sciences is changing these days. And it is the key technology of, let's say, the century in a certain sense, and it will change our society in a radical manner. So it is there to stay. It's not a hype. It has come to stay. And at the same time, it also has many problems, in particular concerning reliability. You've heard of accidents with Tesla cars and also other, let's say, cars which are automatics, problems with security, with privacy, with also responsibility. We don't know how decisions are reached. And so this is actually one main problem worldwide currently, this lack of reliability of AI technology. I'm sure many of you have also used ChatGPT and also witnessed the hallucinations, the wrong answers. Yeah, so all of this is within this, I'd say, problem complex of reliability. Now, I mean, there are certain, let's say, policy attempts in that direction. You might have heard of the AI Act of the European Union. The G7 are also working in this direction, but all of that cannot solve these key problems, because this can only be solved by a deep and profound mathematical understanding, formulating all those questions in a mathematical language. And we will see in a moment how you can do that actually AI is mathematics, period. And so then this leads to many questions in various areas, and then also to very beautiful mathematical problems on their own. So what is AI? Now, so it's actually something quite old, from 1943. McCulloch and Putz wanted to introduce learning, an algorithmic approach to learning. And since we humans believe we are intelligent, so they wanted to mimic the functionality of the human brain. They wanted to develop a mathematical model for the human brain to achieve intelligence. And the human brain consists of neurons which are interconnected. And so they wanted to design a mathematical model for a neuron and then connect it. So let me just explain to you how that looks like. We will then see the precise mathematical formulation also, only that you get an intuition. Yeah, so you have here the incoming signals, x1, x2, x3. They are amplified. So this is mimicked by these weights, W1, W2, W3. Then in this is soma, the sum is collected, so the sum xi, wi. And then the neuron fires or not, and this is mimicked by a bias term, and then the sum is compared to the bias. And here in the easiest case, sorry, if the sum is greater than b or less than b, depending on that, a 1 or a 0 is outputted. It's a bit more complicated. We see it on the next slide, but that's the basic idea. And then, I mean, all these mathematical models for neurons are connected, and the free parameters, which are then, let's say, adapted during the learning procedure, are the weights and the biases. Okay, so let's be a bit more mathematical. So that's the definition of an artificial neuron. We have weights W1 to Wn in R. We have a bias term B in R. We have an activation function, which is rho, which is univariate. And then an artificial neuron is nothing else than this mathematical function, which you see here. Yeah, so comparing to the previous slide, you see on the previous slide, the rho was chosen as the Heaviside function, but certainly you can do it a bit smarter. So this is from the previous slide. We only had output 1 or 0, but you could choose rho to be a sigmoidal function if you want to have something smooth. Nowadays, if you go to the algorithms, usually, I mean, a simple spline function is used to the max of 0 and x, but certainly you can also imagine other types of functions. So this is the mathematical model for a neuron, and then this is interconnected. So just to give you again an intuition here, how this is done. So here we have our inputs, x1, x2, x3, and all of these yellow dots are now these artificial neurons from the previous slide. So what we need to encode are these connections, and you see how it's done. We have here x, and then the first weight matrix encodes these connections. So these two connections are encoded in here. So this times x1, this times x2. Then the second connection is encoded in here, this times x3, and the third also here. So this is weight matrix, and the bias term is added. The activation function is applied component-wise, and then we keep going. So we have now a map from R3 to R2. This is encoded in this weight matrix, and again, we add a bias term and keep going. So I mean, but the key point here I want to make is this neural network is a composition of these affine linear maps, Wx plus b, and these univariate activation functions in between, which are applied component-wise. And so then it's not difficult to imagine what a neural network now is. So a neural network is a highly structured function, which you see here. It consists of the following components of these affine linear terms, these t's, tl, and the activation functions, univariate, which are applied component-wise. And so it's typically depicted in this way. So the number of layers here coincides with how many of these affine linear terms I have. But you can forget all of this. You can just, let's say, look at it as a highly structured mathematical function. So that's what I meant. Artificial intelligence and neural networks are the workhorse, is mathematics, period. It's nothing else. So it's accessible to all of mathematics, which we have. So what are the key questions now, which people ask? And for that, I would like to just take you to the workflow of how neural networks are, are applied. So neural networks are used for approximating highly complex functions if we just have sample values. So we have a highly complex function. Maybe it's defined on a lower dimensional manifold, and maybe it is a function where we want to classify. So then we would have a finite set of outputs, and we have sample values of that. So it could be, for instance, some images in applications and labels, but it can be something very arbitrary. And so now, I mean, we take part of these samples, and we first now need to, so we don't know f, we only know the samples, and we want to use the neural network, which is just a function, as an ansatz function. So then the question arises how we choose our neural network, our class of neural networks, which we now use as an ansatz function. How many layers do we take? How many neurons in each layer? Which activation function? Maybe we don't want to have all connections, and so on. So that's the architecture. We need to set it up, how we choose our class of neural networks, from which we then take the best which approximates that. And so then, I mean, the learning procedure starts. It's an optimization problem, which you see here. You see here, I mean, the neural network function applied to my samples xi. These labels I know, and then I look how close those are. This is this loss function. It could be just a square loss. I sum over all samples and I optimize. And so, I mean, if I do that, then I get my neural network function in the end. So I learn these weights and the biases, as we already discussed before. And I can do everything by stochastic gradient descent, which is a particular optimization strategy. And now this neural network handles the samples I put in very good. But the question is whether I can also recognize other types of data. So for instance, other images. And so what we do then is we take the other set of the samples, which we have not used yet, and then expose the function to those and check whether indeed I get something close to what I would like, close to the function. So this is basically, I mean, the workflow of how I use neural networks. Yeah, so I approximate highly complex functions if I have given sample values, period. Yeah, so it's not more and not less. And these are the main research directions which people are wondering about. So one is what's, called expressivity. We in mathematics would say approximation. So how to set up these network architectures so that from an approximation viewpoint, I get the best approximation rates. This area is purely approximation theory. I will show you one slide later on. Now, because you have a class of, let's say, a parameterized class of functions, and you're wondering how to best approximate, let's say, a specific function which comes from some function class. Then learning. So it's a particular learning procedure, an optimization procedure, the stochastic gradient descent. It's not clear why it works. The problem is non-convex, and still often we get good results. And what people certainly use as tools to analyze this is optimization, optimal control, but also areas, for instance, like algebraic differential geometry, because during optimization, you optimize over a landscape, an energy landscape, and you can also analyze the geometric structure, how flat are the minima, and so on. So people also use these tools these days for that. Then generalization, I now have the test data set. Can I get error bounds, success guarantees? That usually goes in the statistical direction, probability theory, statistics. And then there's another area. If we now have the neural network, we want to understand how decisions are reached. Expandability is also important because, for instance, the EU AI requires that now. That usually uses like uncertainty quantification, information theory. Yeah, but you see, hopefully that most of the areas of mathematics are actually required for analyzing AI. And also another very interesting question is, for instance, are there fundamental limitations? So we used also some, let's say, elements from logic for that. So also that gets involved. There's another direction which I don't want to focus too much here on, which is also AI is used for mathematics. So for instance, for this area of inverse problems, AI are used as solvers. And so this then goes in the direction of imaging sciences, inverse problems, also micro-local analysis comes into play, and also PDEs. So can I solve partial differential equations by artificial intelligence, by neural networks. So then again, neural networks are the Ansatzfunction for the solver. And often it's shown that this can circumvent the curse of dimensionality. We also use it now for actually learning physical laws. If I've given data, can I extract the PDE which generates the data? And interesting enough, there's actually almost no mathematics in this direction, because that's a very unnatural question for mathematics. But you can also already ask questions like, I have data, is the PDE which generated the data uniquely defined? Because otherwise, if you have an algorithm, it's not even clear what it gives. But even that is not known, because these are questions, even in, let's say, abstract theory of PDEs, are very unnatural. But this requires a whole new theory. So let me now give you a short glimpse in some of these directions. For instance, expressivity. So what is the approximation power of the one famous result is the universal approximation theorem. You see it's pure mathematics result. It says I have a continuous function defined on a compact domain. My activation function is continuous, not a polynomial. Then for every accuracy, I find a neural network. And the neural network here looks like this. Yeah, so I have one hidden layer. Yeah, so for every epsilon, for every accuracy, I can show that for that f, I find a network of this type, which approximates the function with this accuracy. Yeah, so there exist all these parameters. I can fill them in so that I get this approximation right. So basically, it shows that Continuous functions on compact domains can be approximated by these type of neural networks with arbitrary accuracy. So this shows some of the universality of neural networks. And so, I mean, you can ask certainly all sorts of questions now if you have deeper neural networks. What can they approximate? Which classes can I approximate with neural networks with 2 layers, but not with 3 layers? And so on and so on. Yeah, so we also went in the direction because for approximation theory, you have this whole area of applied harmonic analysis with wavelets, shearlets, and so on. Can you compare the approximation power of neural networks with all of those systems? And so, for instance, we could show rigorously that neural networks achieve optimal approximation properties of all those systems combined. So they are amazingly universal. They can do basically better than all those systems which we have worked on for many years. Yeah, but I mean, now making this precise and optimizing, I mean, so there are an enormous amount of questions. And again, this is purely approximation theoretic. So then, I mean, generalization is also a very interesting area. It asks, I have trained my neural network on some data. What happens if I now expose it to other types of data? Does it generalize? Yeah, so I have maybe 2 classes of functions or 2 classes of points here. And I add a new point. Does my network classify this correctly? Yeah, so if my expressivity is too low, my network does maybe only, let's say, split this into half. I will certainly misclassify. If my network is a bit better, has a bit more flexibility, I can separate those 2 areas cleanly, and then a new point might be correctly classified. But if the network aims to do the job too good, it encloses the data too much, and then it might be misclassified. And so here, you see, this is what is explained by statistical learning theory. This is very well understood, this picture on the left-hand side. You have here the capacity of the hypothesis class, so the size of the neural network and the error. And the training error you see here, certainly as the network grows larger, the training goes down, error goes down, but the test error goes up. And this is this phenomenon of overfitting. But what we see these days is not this picture, but this picture. Yeah, and so see, as I now increase my size of the neural network more and more, the test error goes down again. And so analyzing this part is actually very difficult. And people use, we see dimensions, there are also neural tangent kernels and so on. So also there, new mathematics is generated and aims to understand this amazing generalization ability. Let me just say, I mean, we also work in this direction. Not going into details, we work for it for graph neural networks. So this is extension where the neural network now takes graphs as an input. And so there we actually derived just very quickly. I mean, we derived a very precise result on the generalization here, the sort of transferability error of the graph neural network, where, I mean, many parts like graph Laplacian consistency error came into account. And I think my time is up. I mean, I think Chris is already making his video visible. So let me just let me just say, I mean, for instance, explainability is also an area where, I mean, there are still very open questions. So here you see a neural network says this is a 3, and then you're wondering why the neural network made this decision. And these explainability approaches produce nice heat maps, which indicate which points were important. But I mean, a lot of mathematics is missing there. So we have also some results using information theory for that. But this requires, I mean, also a lot more mathematics. And maybe just to conclude, I mean, let me not talk about PDEs. I mean, also there we now, as said, using neural networks as ansatz functions. I mean, this also kind of revolutionizes now this whole area of numerical analysis of PDEs, because now you have a specific class of ansatz functions which you want to use. And maybe just finally, let me say, I mean, what we've also showed is that there are problems concerning, let's say, computability for digital hardware. So this goes in the direction of logic. Again, I mean, with mathematics, we could show that digital hardware is one main problem which you can overcome that using analog machines, analog Bloom-Schupf-Smale machines. So in that sense, mathematics really tells you the heart of it. And I think that's the main strength. And let me finish by saying I think AI is there to stay. It's extremely important, and mathematics is desperately needed. There are many directions where everyone can contribute, depending on what your background is. And so in that sense, it's a wide open area, and I think there are very exciting futures perspective. And I think most of the problems which we see lead to their own, let's say, theory. So also the topic of these talks say this goes then from applied mathematics back to pure mathematics and generates its own theories. And with this, I'd like to conclude. Thanks for your attention.